All right, hello everyone. Thanks for being patient with my absence. I've made it here to Georgia, and I'm actually sitting at my grandfather's house in his study right now. He's not using it, and I miss you guys. And I hope that today you stay focused. You can do a lot of learning. I'm making this video to try to help do the things that I would normally do if I was there, to help you through learning our new material at the beginning of Unit 9 around parametric equations and the calculus of parametric equations. So hopefully you have your Unit 9 9.1 packet in front of you. I'm going to lead us through some of the basics and examples, and then at the end of that it'll be your time to practice. My answers are in a PDF document my answers to the practice problems are in a PDF document that you can use to practice. Then you'll work on your concepts, and then at the very end of class, everyone needs to take a quick check-in quiz, not graded, but I want you to do it no notes so that I, even here in Georgia, can kind of see where you're at and know what kind of stuff we need to work on the other side of break. So please stay focused. Try not to get too distracted and get through all the things we need to do today, okay? All right, let's go ahead and get started. All right. So we're going to be talking today about parametric equations, and I know that y'all covered it in pre-calculus, and you had a little bit of review video to do for homework as well. But I'm going to start by talking a little bit about parametric equations in general. We're actually going to start in a second here by sketching a parametric curve. But to remind you, a parametric curve is a curve defined such that x, y, z, and other variables are all functions of some parameter. All right, and a parameter doesn't have to be any sort of special thing, although we use the letter t often to refer to parameters, because often time is a parameter, and say x and y are functions of time, and they kind of move. We can sort of think of parametric curves as allowing x and y to change at the same time, but as different functions of t. You know how so far in calculus we've dealt with like x as a function of t, so something moving back and forth along the x-axis, or even y as a function of t, moving back and forth along the y-axis. Well, if we have parametric curves, we can define x and y as a function of t, and our particle or something can be moving around in the x and y direction, sort of independently of each other, but as a function of t. This means, though, that the resulting curve that we might find might not actually be a true function of x and y. It might fail the vertical line test. You might remember that from past years. But functions of x and y pass the vertical line test. That means that, if you have some curve that's out there, anywhere you draw a vertical line, you would only hit the curve once. That means for every input, there is one and only one output, while the parametric curves we might end up drawing might end up being all kinds of things and might fail the vertical line test and might not actually be functions of x and y. But that's okay. They're still useful for lots of other reasons because motion can be complex. The other useful thing about parametric curves is that it allows us to sort of trace the direction of motion in more complex ways. Because as time passes, maybe our curve here, the particle actually moves this direction and then maybe backs up for a second and moves back and then moves back forward along it. We can keep track of the direction in the actual moment at some moment in time along a parametric curve. So let's go ahead and get started with a sort of non-calculus review of some stuff. This is going to be a little clunky on my part in terms of transitioning between boards, but hopefully we'll be okay. Hope you're having a good day so far. All right. So let's look at that first example that's on there. It says we want to sketch the parametric curve on the given interval, then eliminate the parameter to find an equation that relates x and y directly. And so we have defined for us our parametric curve, which says x, or sometimes you'll see this as x of t. So the x values are defined as 3 cosine of t, and our y values are defined as 2 sine of t. And we want to trace this out on the interval 0 is less than or equal to t is less than or equal to 4 pi. So let's do just like a little sort of thought experiment here, and we'll sort of trace this out for a second. It is hard to hold this and draw at the same time. All right, No judging too much, Nina, please. All right. So super lopsided graph or coordinate axis, but we'll be okay. All right. So the good thing about parametric curves is we can plug in times, t times in here, and plot out what this is going to look like over the course of our time interval. So I'm going to make like a little table down here at times t. We're going to keep track of different, you know what I might do? I have two boards here. Let's be smart. Let's use both of them. And let's keep track in a table of values on our other board here. As t changes, what's going to happen to our x value and our y value over time? And just to kind of speed this process up, let's choose, we're starting at t equals 0. Let's choose like pretty quick things like pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, hopefully we can fit the other things on there, 7 pi over 2, and 4 pi, just to make things fast here. All right. So if we plug each of those times into our x values, our x defined part of the curve, 3 cosine of t, we need 3 times the cosine of whatever we get. So the cosine of 0 is 1 times 3 is 3. At pi, cosine is 0. At pi over 2, cosine is 0. At pi, our cosine value is negative 1. So it's 3 times negative 1. That gives us negative 3. At 3 pi over 2, cosine is 0. 2 pi, cosine is 1. We get 0, negative 3, 0, and 3. So interestingly enough, it looks like our x value hits 3 twice and negative 3 twice. Or sorry, hits 3 times. Wow, can't count. And negative 3 twice. 0 4 times. Let's see what happens to our y values. Remember, our y is defined as 2 sine of t. So the sine of 0 is 0. So it's going to start at 0. And then at pi over 2, 3 times the sine of pi over 2. Sine of pi over 2 is 1. Oh, not 3 times that. 2 times the sine of pi over 2. And pi over 2 is 1. So 2 times sine of pi over 2 is 2. And plug in pi. The sine of pi is 0. So 2 times 0. The sine of 3 pi over 2 is negative 1. So I'll give us negative 2. And then 0. The sine of 2 pi is 0. Sine of 5 pi over 2 is 1. Sine of 3 pi is 0. Sine of 7 pi over 2 is negative 1. So 2 times negative 1 is negative 2. And sine of 4 pi is back to 0. So we actually now have a bunch of points that we've defined here as a function of time. If I plot those out real quick, and you can take the time to do this, I want to be kind of quick here. So it looks like 1, 2, 3. Our points are, if we're tracing a particle, start at, 3, 0. And then at our next instant, it would come up to 0, 2. So it looks like we've kind of traced that direction. And then at a time of pi, it's out here at negative 3, 0. And then 1, 2, we come down here at time of 3 pi over 2, we're at 0, negative 2. And then it's back to 3, 0. So it looks like our particle kind of does this kind of motion here. And we can actually know here in a second that it's more than kind of. But it'll trace out an ellipse. I'm struggling here one-handed. Okay. And it looks like it moved this direction, right? As we traced our points, they traced that direction around the curve. And it looks like, based off of our time interval, that we started at 3, 0. We made it back there, so it did 1 revolution, 2 full revolutions. So it actually, over the course of 0 to 4 pi, we went around our ellipse twice and ended up back where it started, right? So there's a sketch of this parametric curve defined as x is 3 cosine of t and y is 2 sine of t. But let's now go ahead and do the next step here, which is let's eliminate the parameter. That means rewrite this so that it is only in terms of x and y directly, a direct representation with just x and y's left. And for a lot of functions, we can do that. We kind of hope, especially with trig ones, That'll work out kind of easy using some trig identities or something. And it turns out that this one does. You might already be able to tell where this is going. Ellipses work out nicely. So we can use one of our basic identities to say this. All right, let's take 3 cosine of t. Let's take that quantity and square it. And let's add it together with 2 sine of t and square it. All right. Well, let's see. Okay, well, if we square that, then that would give us 9 cosine squared of t plus 4 sine squared of t, right? Let's go ahead and divide this then by 9. Let's divide this by 4. If we think for a second, okay, well, 9 divided by 9, that'll give us cosine of t squared, plus 4 divided by 4, that'll give us sine of t squared. Our Pythagorean identity says cosine squared plus sine squared is going to equal 1. Well, is there a way to turn this then, so that's in terms of x's and y's? Yeah, we could. Really what we started up with here, 3 cosine of t, that was really x, plus 2 sine of t, that was y. So if we rewrite just the numerators here, this was really x squared, and we divided it by 9, plus y squared, ooh, that's an ugly looking y squared, and we divided it by, oh, not 9. Gotta blow on and make it dry a little faster. 4 is equal to 1, but we usually don't write ellipses that way. Instead, we'll write it like this. This is x over 3 squared plus y over 2 squared equals 1. And we just redefined this parametric curve as a direct representation in terms of x and y. It is not a function. It would fail the vertical line test, but there we go. Now, when we start thinking about, well, okay, this isn't calculus yet. This is really just the basics of parametric curves. And you're right, we've not done any calculus yet. But we can actually start going ahead and thinking about some of our calculus type questions we normally ask. So if you look down at the bottom of the page there, you'll see a couple questions I want us to consider here. Let's think. I want to make an observation, and I want us to write down a quick thought about it that will link to what we're going to do here in a second. All right. Okay. Sorry, not trying to make y'all sick here. All right, so observation number 1. If you look at this ellipse, we can tell that if we wanted to, we could talk about a maximum and a minimum in 2 directions. We could talk about like an x maximum and an x minimum, and we can even see those on this curve here. X maximum of 3. We could even see that in the equation over there, how it was x squared over 3. Maximum of x equals 3, minimum of x equals negative 3, and a y maximum of 2, and a y minimum of negative 2, right? So if that's true, then conclusion-wise, there's maybe a few things that we would hope could happen, and it turns out we can make happen. Conclusion for that first row there, maximum, minimum in 2 directions, is that we could find a dx dt and dy dt. We could actually find a derivative independently in the x direction and the y direction to find an x maximum and minimum and a y maximum and a minimum. But we could also, if we want to, we could find sort of an overall derivative, a dy dx, that would relate for us, the slope as a relationship between y and x, as we normally do for other curves that we've done this year. We could even do this for this equation. But we could find a slope at this point here and figure out what its slope is right there if we wanted to. We could figure out the slope right here as in terms of x and y if we want to as well. So we'll get back to how do we do each of these things here in a second with parametric curves. Independently, x as a function of t, just back and forth, y as a function of t, up and down, but then also dy dx, how we're used to doing it. We could also think about, there's a parametric form of the curve and an explicit form of the curve. Well, what do we do with that? The parametric form of the curve is what we started with. The explicit form is what we made down here earlier. with both of those forms, we can do our calculus as we normally can. It is often easier, though, to leave things in terms of parametric form because it allows us to do the work here, dx dt and dy dt, or find things dy dx in terms of what we're sort of used to finding. So we'll often leave things in parametric form and do our work that way. Because if we try to spend time changing stuff over parametrically, it's often easier to leave things parametrically because if we change things over, we end up spending time converting over to be explicit form, and then we got to take derivatives of that. And then we've also kind of, depending on how we do it, lost that sort of relationship to t. All right. And 3. Even just looking at this ellipse here, it looks like concavity changes in slightly more complex ways than we're used to. But we can still find a second derivative and use it to analyze concavity. Remember, the second derivative tells us about concavity. It is not the concavity, but it tells us about the concavity. And we can still do this if we're given parametric curves. All right? Short summary, we can still do things like normal. All right, let's move on. I guess like normal, but the process of finding that derivative will look a little different, as we'll see here in a second. All right. Oh, I tried to cap it, but it didn't work, so we'll leave it open. Okay. Cool. Let's move to the next page there then. Okay. Okay, so top of that next page, slope and concavity. So we have just finished all of our sort of one variable calculus work, which forms the foundation of everything we're going to continue to do. We're going to apply that one variable calculus to what we're going to do in parametric, polar, and vector valued functions as well. And just as we've done all year, we can analyze the slope and concavity of a parametric curve. We can still call the derivative dy dx. We can still call the second derivative, what looks like d squared y over dx squared. So we just need to find a way to differentiate with respect to x as normal if everything is actually defined in terms of t, because those parametric equations are often going to be in terms of t. But we need to figure out a way to write that, take that derivative with respect to x. Keep in mind, if you want to, we can always, as I mentioned, find the derivative of x or y with respect to t and analyze motion in a specific direction, left, right, or up, down, rather than overall. But let's talk about how to find the derivative and second derivative of parametric curves kind of overall, okay? Now let's think about it. Basically what we have here is if we have a function, a parametric curve, x of t, and we have a parametric curve, y of t, you can put this in the blank spot down underneath, but leave some space because we can do the first and second derivative. Then if we want dy dx, we can think about it this way. Well, we know how division works, and we're now used to these differentials. So if we want to, we can define our first derivative of y with respect to x in terms of parametric curves as this, dy dt. So take the first derivative of y with respect to t, so take the derivative of y with respect to t, divide it by the derivative of x with respect to t. If we do that, this is not quotient rule or anything, but if we take the derivative of y with respect to t, divided by the derivative of x with respect to t, we get dy dx. But that makes sense if we just think about how these differentials work in terms of division. Dividing by dx dt is the same thing as saying dy dt times dt dx. It's basically like the chain rule, and we get dy dx, okay? So this is kind of our big rule for today around derivatives of parametric curves. Take the first derivative of y with respect to t, divided by the first derivative of x with respect to t. But then you go, well, okay, how would I take the second derivative? Okay? In other words, we want this, right? Okay. Well, we got to think then about how we make the differentials work. And here's how it goes. If we take then the derivative with respect to t, because in the end here, this first derivative you find will actually still be in terms of t, as we'll see, because we're just dividing these two things, so there'll still be t's involved. If we take the derivative of that derivative we've already found, if we take that first derivative, we take the derivative of it with respect to t, and then we divide it by the derivative of x with respect to t. So basically take the derivative of what we got up here, again, and then divide it by the derivative of x with respect to t, which we actually already needed to find to do this. Then this gives us the second derivative of y with respect to x. We can think about how that makes sense with the differentials. If we do this sort of manipulation again, we get the derivative with respect to t of dy dx. But dividing by dx dt is really multiplying dt over dx. Oh, that's an ugly x, but that's an x. I'll erase it because I'm embarrassed by that. Okay, then we would, if you see here, manipulation, we'd lose those dt's, and we would get here the second derivative, d times d. If you've ever wondered why we put the squared in front of the d, that's why. D times d squared y. D squared y over dx times dx will give us dx squared. All right, so here are our two big rules, and we're going to see them in action here in a second. First derivative of y with respect to x, take the derivative of y with respect to t, divided by derivative of x with respect to t. For the second derivative, we do the derivative of that thing we just found with respect to t, but then divide it by the derivative of dx dt. These are new rules. They're not quotient rule things we're used to. New rules to remember, okay? All right, let's take a look at a practice problem here, and I think y'all will all be set. Hopefully none of what I say causes a fight between Tweeby and Steven like it did that one time. Okay, I'm going to erase both boards because that'll make things easier to talk about. So we're going to look at that problem at the bottom of page 3 that's there, okay? It says example 2. All right, example 2. Oh, man, okay. Cool. Consider the parametric curve defined by x equals, can't even see that, x equals t squared minus 4, and y equals 2 sine of t, and we're looking at the interval 0 to 2 pi. All right, I want to sketch a graph of the curve. We can do a t column, an x column, a y column. We can have to do maybe a little more thinking this time because we got like trig-related interval here, which makes sense for our y values. And then we have something that's not a trig-related interval, but we can choose some points that are nice and some points that aren't. Let's say we do like 0 and 2 pi obviously in there will work. And then, I don't know, we can choose like sine, or whatever. I guess we can do like let's start with our trig ones and we can just kind of estimate from there. Pi over 2, 3 pi over 2, and we'll go from that. All right. So plug into our x, 0 squared minus 4 will give us negative 4. All right. Pi over 2 squared. I'm going to have to do some calculations here. Pi over 2 times pi over 2 is going to give us 2.467. We're going to subtract 4 from that. Minus 4 is going to give us like negative 1.53-ish. All right. So we can do that again. We can do this time 3 pi over 2 times 3 pi over 2. And then we'll subtract 4. All right. This time is going to give us something bigger. It's going to give us 18.2. And then finally we have 2 pi times 2 pi. 2 pi times 2 pi. And then we'll subtract 4 from that. Gives us 35.47, 35.47. So our x values get bigger, 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 and it looks like they're getting bigger pretty fast. But that makes sense for squared stuff, right? Our y one should be a little easier to take care of. So sine of 0 is 0. Sine of pi over 2 is 1, so that'll be 2. Our sine of 3 pi over 2 is, oh, I guess I forgot pi in here. That would have been, okay, we can squeeze a pi in that. Our sine of pi then is 0, so that takes us back to 0. And let's see, what else? Sine of 3 pi over 2 is... Sine of 3 pi over 2 is -1. Sorry, so that takes us to -2. And then 2 pi, sine of 2 pi is 0, so it takes us back to 0. I guess I got to go back up and fill in this x value for pi. So that'd be pi times pi, that's pi squared. And then subtract 4. It'd be 5.86, 5.86. All right, so we graph something like this. For the sake of making things a little easier here, I'm going to do a small change. Let's only graph this then from 0 is less than or equal to t to pi. Make things a little quicker this way on the graphing. All right, so -4 zeros are starting point, 1, 2, 3, 4 out there. At pi over 2, we're at a value of -1.53 and then up to somewhere there-ish, right? And then at pi, we're way out here at 1, 2, 3, 4, 5, almost 6, value of 0. All right. I've traced this one before, so I kind of know what it looks like. It looks a little funky, but it kind of does this shape. Oop, kind of a little slanty there, too much. It does this kind of shape. It kind of comes up that direction and then back down. All right. Okay. I guess its peak, though, if I can adjust, its peak is not, in fact, at an x value of 0. It's a little steeper than that. It kind of comes up. Two up there. There we go. Somewhere up in that range, and then comes back down. All right. So our graph kind of comes up and slants back down that direction is what we're looking at. Okay. So we've not done any calculus yet. We've just kind of sketched that. So let's see. Now we want to find the highest point on the curve. Well, see, highest point. Highest point, that sounds like a maximum in our y value. Okay. If I want a maximum in my y value, all I care about then is this part here, the y value. If I want a maximum, that sounds like I can look at my derivative. So let me find dy dt. What is my maximum y value? Well, my maximum is going to happen when dy dt changes positive to negative, right? That's when a maximum happens. When dy dt changes from positive to negative, my y value will have a maximum. So let me find dy dt. dy dt, that's easy to do. The derivative of y with respect to t to cosine of t. Okay. And let's keep looking just at the interval 0 to pi. If I want to find when does cosine change from positive to negative, if I'm thinking about that, cosine changes from positive to negative at t equals, right, changes from positive to negative at t equals pi over 2, right? At t equals, I'm going to make that nicer again. Ooh, that didn't make it nicer at all. At t equals pi over 2. All right, so that's the time when our cosine changes from positive to negative. So that's when dy dt will change from positive to negative. But we want, for this question, find the highest point. So then we need to take this and we need to plug it into our equations if we actually want the point up here. But wait, we've already plugged pi over 2 into both of those. So at pi over 2, our point was -1.53, comma 2 is the highest point on our graph. So that's how we can use the derivative of y with respect to t. We've not actually done anything fancy there to find, to analyze something in terms of motion just vertically. Highest point. We could have also done that lowest point, or farthest left, farthest right. For farthest left, farthest right, we would just use dx dt instead of dy dt. All right, so move over here. Let's find dy dx now, and that's part C. Part C says find dy dx. All right, dy dx, that's when we need our new formula. Our dy dx in these parametric curves is defined as the derivative of y with respect to t divided by the derivative of x with respect to t. So we have to find those separately. dy dt, the derivative of y with respect to t, the derivative of y, we already said, was 2 cosine of t. What is our derivative of x? Dx dt then, our derivative of x with respect to t, we go back to our x defined part of the curve. The derivative of x with respect to t is 2t. So what is dy dx? That means dy dx, we simply divide the two of them. Dy dx is 2 cosine of t divided by 2t, which would give us cosine of t divided by t. That is our derivative of y with respect to x. Notice it still has t's in it. That is fine, but it will give us the slope of the curve at any time we want to give it. Doesn't mean we may have to do some back and forth, because if we don't know the point, we may have to solve for t first before plugging t in to find dy dx. But that'll be okay. That's usually not too hard to do. Finally, it says find all the points of inflection on the curve. Find all the points of inflection. Well, points of inflection come from when the second derivative changes sign. Second derivative changes sign, right? Second derivative changes sign. So the second derivative changes sign. That means we need the second derivative. That's where we got to go to our second derivative formula we talked about. The second derivative formula says, okay, if we have our first derivative, we now need to take the derivative of this with respect to t. Got to do that first. Take the derivative of this with respect to t and then divide it by dx dt. So let's see, we need this derivative. That looks like a quotient rule thing, right? So this is going to get kind of complicated. All right, let's do it. The derivative of cosine of t over t, that means low. Derivative of the high means negative sine of t, minus high, d low, which is 1, so I won't write it, all over low squared. So there's the derivative of dy dx with respect to t. That's the top part. Whenever we take the second derivative parametrically, we take the derivative of dy dx, which is right there, and we divide it by what we got for dx dt. We divide it by dx dt. dx dt, we already know, is 2t. We can clean some of this stuff up. Telephone's ringing. This is what happens when you're in your grandpa's office. So we clean this up. We get negative t sine of t minus cosine of t divided by, bring that divided in there, gives us 2t cubed. And there we go. So this here is our second derivative, found by taking the derivative of the first derivative with respect to t, what we got up here, and then dividing it by dx dt. That's the process every time. So here's your second derivative. This is what we would need now to look at to figure out when then the second derivative changes sign, because that's the definition of a point of inflection. So this is where sometimes we will need to calculate. This becomes pretty difficult to evaluate without a calculator. So I'm going to go here. Most of the problems that I have designed for y'all today, you do not need a calculator for. I'm going to cheat for a second here to speed things up. And we're going to go ahead and I'm going to go ahead and graph what we got here. Negative, adjust here, negative x, sine of x.
February 6, 1937. 5300 Zebulon Road, Unit 15, Macon 31210.
Sorry about that. He's obviously got a lot of things to take care of now that his wife has died. That's not meant to be sad, but it is the reality. All right, and we finished graphing that. All right, so we get, after I graph this, negative x, I'm calling it x, but it's t's in our minds, minus cosine of t over t. Ooh, I put the cubed in the wrong place. We don't want to cube the whole thing, do we? We just want to do 2x cubed. Doesn't change it that much, but there we go. Okay, so we now need to figure out on the interval 0 to pi. So if I zoom in on the interval 0 to pi, where does our second derivative graph change sign? And it looks like it changes sign at 2.798. T equals 2.798. All right, there's our point of inflection. Now you kind of know how to do everything. You can take the derivative of a parametric curve, you We can find the second derivative. We can use it to analyze things. It's not too bad. To help you out with one last thing, I do want to show one more quick problem. So if you flip the next page, you will see there part of a free response question from a few years ago, that I want to talk about real quick, okay? Okay, so a particle moves along a curve in the xy plane, time is greater than 0, and they give us dx dt. So there we go, we're told dx dt is 6 over t minus 3 to the 1/3. And we're told dy dt is te to the negative t. Right? All right. So we're given that, and let's figure out what they ask us to discover about it. All right. Okay. They tell us at time t equals 3, the particle is at the point. Oop, it says 5, 4. I started to write a 3. Have no idea why. 5, 4. Okay. I know why, because that was 3. So we got derivatives in both directions. We know a time. We know a point at that time. Write an equation to the line for the line tangent to the graph, tangent to the path of the particle at t equals 3. Tangent lines. Well, we know how to write tangent lines, right? We know how to write tangent lines. Tangent lines, we need a slope and we need a point. Well, we have a point. The point is 5, 4, so that's not too bad. We just need to figure out the slope, but we know slope means derivative. All of our normal slope things apply. So if we have a place, for example, where the derivative does not exist, it might mean we have a vertical tangent line, things like that. So we can still find slopes of tangent lines here. We would need to figure out the derivative. When we're given the derivative dx dt and dy dt, we need to find dy dx then. Okay, so how do we find dy dx? Well, we have our formula for it. It says you take dy dt and you divide it by dx dt. That'll do it for us. So dy dt is up here, te to the negative 1, or negative t, over. Then we divide the derivative we got there, which they already gave us, by the derivative of x with respect to t, which is 6 over t minus 3 to the 1/3. Okay, so there's our derivative of y with respect to x. But we need the slope at this point, but we're told that that point happens at this time. So we can take that time and plug it in here. Sometimes we have to solve for the time, but in this case we just have it. So we can go ahead and plug that in. This gives us then that we're really looking at 3e to the negative 3 over, let's see, 6 divided by 3 is 2, minus 3 gives us negative 1 to the 1/3. We simplify that, we get the value 3e to the negative 3 over negative 1 to the 1/3. The cube root of negative 1 is negative 1, so why not just call that negative 3e to the negative 3, okay? So we've gotten our slope now. Hopefully we can put this all together, okay? So we got a slope, we got our point. Let's remember our formula. We need y minus y1 equals, now we need m, which is negative 3e to the negative 3. And then remember x minus x1. So we can go in and substitute in what we know and finish off this equation. Sorry, just looking up one thing, make sure I got all the things I need for y'all. Okay. There we go. Okay. Cool. So, perfect. Times x minus x1, and there we go. That would give us the equation of the tangent line right there. Y minus y1 equals mx minus x1. Okay? Pretty good. Not too bad. So at this point, you have everything that you need to take care of your work for today. Please stay focused. Try the practice problems now. My answers are below. Then move on to the concepts to practice, and make sure you finish up the practice quiz or the check-in quiz by the end of the period. Homework is also posted, but the answers are not up yet. If you need extra help, I will post at least one, I'll post some other things below in case you need a little extra help, okay? Thanks for your time. Stay focused, and I'll see y'all soon. Good luck. Love you guys.